All right, this is going to be a video on solving the practice problems with electrical circuits. So we're going to work through these two problems, the first one and our second one. And the second one is very similar to our fan situation in our house project. So beginning with this problem, we have two light bulbs, one rated 30 watts and the other rated 40. Now, the number one thing I want to point out here is the wattage rating for the two bulbs is dependent on the voltage that it's connected across. But what you're saying there is if connected to 120 volts, it will produce 30 watts of energy in light. The same thing with the 40-watt light bulb, you get 40 watts if you connect it to 120 volts. So just like in the project, when the voltage wasn't as high, the bulbs weren't as bright, right? So that's only true for when you connect it to the 120 volts. However, that wattage rating is dependent on the resistance of the bulb. So throughout this problem, keep in mind we're going to use those values to calculate the resistance of the bulb, but the bulb's resistance does not change, nor is it dependent on how it is connected in the circuit. That's kind of like asking the color of something. It stays the same, the size of something, the mass. Any of those are characteristics of the material itself, and that is on the resistance. So we can change resistance with the diameter of the wire, the coiling of the wire, and things, but in the bulb itself, that resistance will remain constant. Okay, so taking a look at that problem, first question, two bulbs are first connected in parallel. Determine the resistance of the bulb rated to 30 watts and the current in it when it is connected in this circuit. So we're going to do the same thing with the 40 watts. So if I'm going to connect those in parallel, go to our whiteboard. So if they are connected in parallel, what does that circuit look like? And we are going to connect them across a voltage of 120 volts. So one light bulb, two light bulbs. So 120 volts, which means each of these are going to get the 120 volts, and their power is going to be 30 watts and 40 watts. So I'm going to call those bulbs 1, 2, 1, and 2, just to distinguish which ones I'm talking about. All right, so for part 1 in our problem, what we do know is that the voltage across bulb 1 is equal to 120 volts, and the power rating of bulb 1 is 30 watts. We're looking to find the current in bulb 1. So just simply applying the equation of P equals IV. We will solve for current. Rearranging the equation, we get current is equal to power divided by voltage. So current of bulb 1 is equal to the power of bulb 1 divided by the voltage of bulb 1. Since those are the values I have, I can keep that equation like that and say 30 watts divided by 120 volts gives me the current in bulb 1 equal to 0.25 amps. Then we were asked to find the resistance of the bulb. So that tells me the current. So that's the current that's going to come out and feed this line right here. Right? So that's going to be 0.5 amps. 0.25, sorry. 0.25 amps. So knowing that, then resistance from the equation V equals IR, resistance is equal to voltage divided by current. So the resistance of the 30 ohm bulb, which we call bulb 1, is 120 volts divided by 0.25 amps. So its resistance, I get to be 480 ohms, which was our first question. So keeping in mind that resistance will not change no matter the voltage that I used to put across there, no matter the current. That resistance will remain constant, but now I can solve for voltage and current in different situations. For the second part, what about the 40 ohm or 40 watt bulb, right? So now we have power of 2 is 40 watts. The voltage of 2 is still at 120 volts. We can solve for the current of 2 that goes into that branch using the same equation we did up above, where current 2 is equal to power 2 divided by voltage 2. So that's going to be 40 watts divided by 120 volts. So the current that the 40 watt bulb is going to draw in that circuit is 0.33 amps. Using these same equations for resistance, R2 is going to be V2 divided by I2. So resistance of the 40 watt bulb is going to be 120 volts divided by 0.33 amps. Bulb 2 has a resistance of 363.4 ohms. So we're going to round that to the 363. Okay, so that's parts 1 and 2. Going back to the question now. Next part, what if I connect them in series to each other to the 120 volt source? Determine the resistance of the bulb and the current when it is connected in the circuit. Same thing for part 2 there. So again, this resistance of the bulb that we just calculated doesn't change, even though we're changing the voltage of the bulb, right? Because it's connected now in series. But I'm going to take those same bulbs, and because they are the same bulbs, I cannot change the resistance of the bulbs. And now I'm going to connect them in series. So what's going to happen now is they're going to draw a different amount of current, right? So we have our 2 bulbs in series. This one having a resistance of 480 ohms and 363.4 ohms. We're still using 120 volts, but since they are in series, remember, the voltage splits up. So they're not going to get that amount of voltage. These are going to be dimmer. So they're not going to operate at the full 30 watts or 40 watts. So I can't use the same current. I can't use the same voltage. I can't use the same power. The only value that can carry over into this part is resistance. So again, if I call these bulbs 1 and 2, I can still say that the resistance of bulb 1 is 40 ohms, and the resistance of bulb 2 is 363.4 ohms. So what I can find, since they are in series, is my resistance is going to add. Our total is going to be R1 plus R2. So that's going to be 480 ohms plus 363.4 ohms. So my total resistance comes out to be 843.4 ohms. Now I'm going to use that total resistance, right, to then find what is the total current coming out of the battery. So we can look at this as one light bulb having a total resistance of 483.4 ohms, and my voltage being 120 volts. So now the question becomes, how much current comes out of here? Because that current that comes out must go through each of the bulbs, right? So the question is, how much current is coming through each one? And what we can recognize is I total is going to equal I1, and that's also going to equal I2 because it's in series. So I total, what we do know is that V total, do you know V total be 120 volts? We know R total. So I can say here that I total is equal to V total divided by R total. So remember when you use Ohm's law that each of the subscripts must be the same. So I total is going to be 120 volts divided by the 483.4 ohms. That gives you a total current equal to 0.14 amps. That will be the current through both of those. Okay. So once I find that, I found the current through each of those when wired in series. Okay, so that was the second half of that question. When these are wired in series, they're going to have the same current, and that current has to be determined by the total resistance in the circuit. All right, next part of the question is asking, rate the brightness, right? So if those are my choices of how I would wire these up, I look at these circuits, right? We do know that the parallel is going to give us the brightest bulbs, right? So the brighter one would be the one that has the greater power rating. So in this case, these are going to be the brightest bulbs, right? Of these two. The series and parallel. So within this, then we would say the 40 watts has the greatest power rating, right? So ranking them in order, 1, 2, 3, 4, you have the 40 watt bulb in a parallel circuit. Then you have the 30 watt bulb, right? And then we come down here and we ask ourselves, which one has the greater power down here? So in this scenario, what we would say is, because the currents are the same, I1 equals I2, but R1 is greater than R2, and V equals IR. If this variable is the same, and the R value is greater, then the one with the greater R value gets the greater voltage. So that means V1 is greater than V2. Since power is equal to current times voltage, and again, current is the same, the one that has the greater voltage will have the greater power. So that means P1 is greater than P2. Okay? So the 30 watt light bulb, surprisingly, in a series circuit will give you the greatest power. So on your chart, if we go back to your chart, this should be in order of 1 would be the first bulb, 1, 2, 3, and then 4. And hopefully by explaining it this way, that makes some sense to you. All right, next part of the question. Calculate the total power dissipated by the two bulbs in each of the following cases. What was the total power in parallel, and what's the total power in series? So if we go back to here, again, on the power equation, you can use the same formula to say that power, using the same scrub suit, power total equals current total plus voltage total, or times voltage total. So in the parallel part, we need to find I total. We do know that V total is 120 volts. I total is what we don't know yet. How much current does each one draw? But we calculated that up here, right? So we said we'd get 0.25 from the first bulb, and then 0.33 from the second. Okay? So I total is equal to I1 plus I2. So that's going to be 0.25 amps plus 0.33 amps. Those are going to be our two currents. And this will give us a total of 0.58 amps for I total. 0.58 amps. So if we come down here, our total power dissipated, this would be 0.58. So now in parallel, our total power is equal to 0.58 amps times 120 volts. So that total power is 69.6 watts or 70 watts. Notice that out also equals P1 plus P2. So parallel, if you know the power of each branch, you can just add those. In series, though, if we take a look at series, power total equals I total V total. So we're going to know that in the series, we found that total current to be 0.14. So this is 0.14 amps. My total current is still 100, or total voltage, 120 volts. So the total power dissipated in a series circuit is 16.8 watts. So you can clearly see, wow, what a difference, right? More than 3 times more the amount of power given off in the parallel circuit compared to a series circuit. All right, hopefully that helped you on this first problem. There's all your work there. You can find those solutions under our class handouts. Now, if we take a look at our second problem, we have a bulb designated to dissipate 6 watts when it is connected to a 12-volt source. So keep in mind, that's when it gets connected to 12-volt, we get 6 watts. What is the resistance of this light bulb? If the light bulb functions as designated, meaning if it gives off 6 watts of power and is lit for 30 days, how much energy is used? Okay, so remember that power is energy per time. It's joules per second. How much energy is given off per time? The last half is pretty quick as far as just deciding how would I have to connect these for all of those scenarios to work. So right away, the red flag is we have a 12-volt light bulb, but a 120-volt power source. So that's not good. That would definitely blow out that light bulb. So let's begin in the first part. So number 2. So we take a look at number 2. So we know that the power is equal to 6 watts. The voltage is 12 volts. We want to know the resistance of the bulb. So power is equal to current times voltage. So resistance is equal to power divided by voltage. Resistance would, I'm sorry, too fast, going way too fast. Power equals current times voltage. Resistance is equal to voltage divided by current, right? That's what we're looking for. So I do know my power and my voltage. I don't know current. So we want to get rid of that variable. So power divided by voltage is equal to your current. So I'm going to plug that into here to say resistance is going to be voltage divided by power over voltage. So it's going to be V squared divided by P. V squared divided by P. So my total resistance here is going to be 12 volts squared divided by the power of 6 watts. So that gives me a total resistance equal to 24 ohms. Total resistance of 24 ohms. For part B, taking a look at that, how much energy is given off in the time of 30 days. So the question here is how much energy is equal to 30 days if you have 6 watts of energy. So remember that 6 watts is equivalent to saying there's 6 joules given off every second. Now remember that joules is the unit of energy. So 6 watts gives you 6 joules per second of energy. So this is all dimensional analysis. How much energy is equal to 6 joules per second. Right, so we want energy given in 30 days. So we want to leave the energy of 6 joules and convert seconds to days. So we do know there's 3,600 seconds in one day. Right? But here we have 30 days. So the days cancel, the seconds cancel, and we're left with just units of joules, which is what we want. So this is in units of joules. So just multiplying everything, 6 times 3,600 times 30, I get 1.56 times 10 to the 7th joules. All right, this last part here. How would I connect these to make this work? So an adjustable resistor means you can determine whatever value you need in the resistance to use in the circuit. So in this case, we know, okay, this gets 120 volts. So we know that we want that connected directly to the power supply, right? This only gets 12 volts. So we need something in there to share the voltage. And that's where we will then connect it in a parallel circuit. Right? So I still want to come out my power supply, go through the bulb, have to go through the resistance, and then get back to our bulb. Set every bulb. In symbol form, what that's going to look like is you're going to have your power supply, 120 volts. You're going to go through a light bulb, right? That is also connected to the resistor. And you're also going to operate the toaster next to it. So that's what that looks like, right? So one thing you want to keep in mind is current's going to come out of here, go through the first branch, but you're also going to get current coming out and going into the second branch. Right? All right. And what I would like you to do here is then calculate how much resistance do I need the variable of the resistor to be? What would have to be the value of that resistance? So again, redrawing our circuit, a light bulb with a variable resistor, that symbol you just kind of make like that, along with a toaster. Right? Now, what we do know, if this is 120 volts, then this path gets 120 volts, right? And this path gets 120 volts. So both pathways get 120 volts. That's okay for the toaster because it operates at 120 volts. But we need our light bulb to only accept 12 volts. So what we want is this to be 12 volts. So that means when the current goes through and it goes through, it loses up 12 volts. What's left is given up by the variable resistor. So I need that to have the value of 108 volts. Because if I were to number those, right, everything in the circuit gets confusing. 1 and 2 and 3. What I do know is that I want this branch right here. V total is going to be equal to V1 plus V2. So V total is equal to 120 volts. V1 is equal to 12 volts because that's the rating that we wanted, which means V2 is going to be V total minus V1. So that's going to be 120 volts minus 12 volts. So V total, whoops, V2, I should say, not total. V2 is equal to 108 volts, subtracting those two values. So this is what you would be doing in the lab. We know that the motors are operating at 3 volts, and we need that to slow down. We want more current to go through, so it is a slower fan. So V2 is 120 volts. How much current do we want to go through that path, right? So what's the current that's going to go through that? Or what do I need the variable, the resistor, to be? So the current that we want from the bulb, so if the bulb was to operate at 6 watts, 12 volts, remember that its current, as we calculated up at the top, was equal to 0.5 amps. That's what we want from the bulb. We want it getting all 6 watts of energy. To do that, it's going to need a current of 0.5 amps. Well, if I need that to have a current of 0.5 amps, that means the current that goes through the bulb, which is 0.5 amps, must also go through a variable resistor. So we want the resistance also be 0.5 amps. I'm sorry, the current I2 to be the current that's passing through. All right, so we want I2 to also be 0.5 amps, right? So we need this to be 0.5 amps. So that means, what is the resistance of our variable resistor? In this circuit, I'm calling it number 2, right? That's my variable resistor. So the resistance of that has to be the voltage that I needed to have, V2, over the current that I needed to have. So this is going to be 108 volts divided by our 0.5 amps. So 108 volts divided by 0.5 amps. So R2 is equal to 216 ohms. So remember, this 108 volts is the result of the 120 minus the 12, because that's what the bulb will get. This is because I1 must equal I2, and we need the bulb to get 0.5 amps to operate at 6 watts. Okay, so just reminding you of how we got those values. All right, so that takes care of problem number 2 as well, keeping in mind of how we connected this. It's a little easier maybe to look at it in this diagram form. All right, hopefully this helps in solving additional circuit problems.